Hello, this is Mr. P, and today we're going to learn about conic sections. Specifically, we're going to learn about circles and parabolas. And we're going to take more of a geometric approach to these than what you might have seen in Algebra 2. Algebra 2, you're given an analytic approach, and here we're going to look at the geometry of these curves. First of all, this equation here represents the general form of a conic section. Any one of these shapes is going to fit into this equation with A, B, C, D, E, and F being coefficients. And geometrically, I want you to first understand how these shapes are generated. So if we take an axis, and we take a straight line to be our axis, and then we take another line that intersects that line, then we're going to hold the axis fixed, and then for the other line, which is referred to as a generator, we're going to rotate it around 360 degrees, or 2 pi, about the intersection. So the intersection will stay fixed, and this blue line will rotate around, and it will sweep out the surface of this cone. And notice how this cone has two parts to it, which are called naps. This is a double napped cone. So it comes to a point in the center where you have the intersection of the generator, which is the blue line, and the axis, which is the dotted line. And as you rotate it, sweeps out the double nap of the cone. Now, all of our shapes for conic sections are cross sections of this double napped cone and a plane that intersects it. And depending on how it intersects it, it will create these different shapes. First of all, if the plane intersects the cone so that in a way that it is perpendicular to the axis, but not through the center there, then it will create a circle. So if we get rid of those, you can see that it's going to create this circle right here as this cross section. If it crosses through the cone in any angle other than perpendicular, but only crosses through one of the naps, then it is going to be an ellipse, unless it crosses through at a very specific angle so that it is perpendicular to another generator. For example, here's a generator. If the plane is, not perpendicular, parallel to a generator, then it's going to create a parabola rather than the ellipse. So you can see the circle, as you skew it, it's going to open up, become a parabola, and then eventually, if we're holding this point fixed through the rotation, and eventually when you rotate it enough, if it intersects two of the naps, both naps, then you're going to get a hyperbola. This would happen when the plane itself is parallel to the axis. If we think of the axis going through the center, and this is three-dimensional, so the plane is coming out at us here, and this plane will be parallel to the axis, will not cross the axis. These are the four main shapes for conic sections. But there are some other shapes which aren't typically thought of as conic sections, but they are degenerate forms of a conic section. Because if that plane does go through that center, then the only place where the intersection is going to be a point. So a point actually is a degenerate form of a conic section. Likewise, a line is anytime the plane actually contains a generator. So this line, if you have the plane going right in the angle where it contains that line, then the cross-section will be that line. And in this case, where we had the plane parallel to the axis, but not touching it, if we actually back this plane up until it includes the axis, then that's how you would get a pair of intersecting lines. So these three aren't typically thought of as conic sections, but they are actually conic sections. Now let's look at our geometric definitions. Today we're going to work with circles and parabolas. So our geometric definition of a circle, it's the set of all points. It is a set of points. It's a set of all points that are equidistant from a fixed point, which we call the center. And we typically use h and k to denote the coordinates of the center. H is your x coordinate, and k is your y coordinate of the center. So it's from a fixed point, we have a certain distance, which we're going to call r, and that we're going to refer to that as the radius. So if you notice from the standard form of the equation here, all we need to know to be able to write the standard form is where the center is and what the radius is. Once you know those two, you can put them in this model and you have your equation of a circle. Also notice that if h and k are both 0, then you have a nice simplified version of this, which is x squared plus y squared equals r squared, which is an equation you should be very familiar with everything we did with polar equations. Alright, so let's look at an example of what we need to be able to do here. Let's say we're given the point 1, 4 is on the circle, and they tell us the center is -2, -3, and they want us to write the standard form of the equation of the circle. And here's a diagram that shows you visually what we're looking at. -2, -3 is the center, and 1, 4 is on the circle. So like we said before, all we need to know is the center and the radius. They're given us the center. So to find the radius, we simply look what is the distance from the center to the edge of the circle. In other words, what is the distance between these 2 points? Well, luckily we have a nice little distance formula for that. And for the distance formula, you simply take the 2 points and you take the difference of the x values and square it, difference of the y values and square it, add those squares together and take the square root. You'll notice that the distance formula is nothing more than the Pythagorean theorem in disguise. And when you do the algebra and simplify, you get down to square root of 58. So now we're going to choose our model, which is that standard form. And we're going to substitute in h and k. Notice how you're substituting in negative numbers. And then with r, notice how r is square root of 58, but the model calls for r squared. So when you square the root of 58, you get just 58. And you clean up the negatives to be positives. And at this point, it always helps to have a little check of, does my answer make sense? And the check you're going to make here is the h and the k, the coordinates of the center of the circle. Those are going to be the values that cause these parentheses to be 0. In other words, for my x coordinate, what is the value of x that causes this parenthesis to be 0? Well, that would be -2. That is the x value of my center. What's the value of y that causes this parenthesis to be 0? Which is -3. That's the y value of my center. So it always helps to make a little reality check at the end. All right, let's look at one more example of this. And this time we have a center is -3, -5, and the point is 1, -2 that is on the circle. And this one we're just approach it analytically. I'm not going to draw the picture on this one, because first of all we just want to find the radius, which is the square root of the difference in the x squared plus the difference in the y squared. And when I do that, you can check the arithmetic yourselves. But when I do that, got ahead of myself, you'll notice that you have the radius is 25. Now, once you notice that your sides are 3 and 4, or your differences are 3 and 4, remember this is the hypotenuse of a triangle with legs 3 and 4. So hopefully you should recognize that you're dealing with 3, 4, 5 triangle. So 5 is the radius. And now we know the radius, we know the center, so we take our standard model and we substitute in the values we know, and we get our equation. Notice how if r is 25, then r squared, if r is 5, then r squared is 25. Also notice how -3 is the value of x that causes that to be 0, which makes sense with our center. -5 is the value of x that causes that to be 0, which makes sense with our center. Alright, the next skill we need is being able to sketch a circle. And very often you'll be given the equation in general form. It's not already in the standard form for you. So we'll have to manipulate this so that it is in standard form. So first thing we're going to need to do is complete the square for x and complete the square for y. And I'll show you the algebraic steps here. We're going to take the original equation. We're going to group the x terms, group the y terms, and I'm going to take this constant and bring it to the other side, which makes it a -6. And then for the x terms, I'm going to look at the linear coefficient, which is -6. I'm going to divide by 2 and then square it. So -6 divided by 2 is -3, and when I square it, I get +9. So I add 9 to complete the square, which means on the other side, I have to also add 9 so that I preserve equality. Now the interesting thing here is it doesn't even really matter the sign, the SIGN sign of this coefficient, because when you square it, it's going to become positive anyway. So if you look at the y's, I can simply think of it as 2 divided by 2 is 1, squared is 1, so I add 1 on both sides. And then cleaning this up, we simply factor this as a perfect square. I know it's a perfect square because we just made it a perfect square. And don't forget that the sign in the middle will be the same as the sign in the middle here when you do the factoring. So that is our standard form of the equation. And now we're going to compare this with our model and realize that the value of x that causes that parenthesis to be 0, that'll be the x value of the center. The value of y that causes that to be 0 is the y value of the center. And then this represents r squared. That means the radius is 2. So to sketch the circle, first you want to plot your center. And then the easiest way is you take this distance and you go left, right, up, and down to make these 4 points. And then draw a circle through those 4 points, and that'll be good enough for a sketch of the circle. And let's look at one more example of this. I'm going to give you multiple examples here. Remember, you can pause this if you want to work the example yourself. Here we're looking at, again, sketch the circle. They give it to us in general form. So I want to group the x's, group the y's, bring the constant over to the other side, which makes it positive. And then completing the square for the x, I divide by 2 and square it, which gives me a 1. 2 divided by 2 is 1, 1 squared is 1. And then here, 4 divided by 2 is 2, 2 squared is 4, and make sure that you add those to the other side as well to preserve equality. And cleaning up a little bit, we combine like terms, which make that 9. This factors to be x minus 1 quantity squared. This factors to be y minus 2 quantity squared. And now we're looking for what is the value of x that causes that parenthesis to be 0, which would be 1. Value of y that causes that to be 0 would be 2. So my center is 1, 2. And this represents r squared, which means r is 3. So we have a radius of 3. And from there, the sketch comes naturally. We plot the center at 1, 2. And then 3 units left, right, up, and down give us those other 4 points. And we draw our curve through those 4 points. All right, next we're going to look at finding the x and y intercepts. So they ask us to find the x and y intercepts of the circle given by this equation. And the important thing to remember in general is the easy approach to intercepts is when you're finding an x-intercept, you're solving for x. When you're finding a y-intercept, you're solving for y when you let the other variable be 0. So in other words, if I want an x-intercept, then I'm going to set y to be 0, which we did right here, and then solve the resulting equation. So here, -2 squared is 4. Bring it to the other side, makes a -4, apply it to the 16, that's how you get your 12. And now we can take the square root of both sides, and when you do that, don't forget the plus minus. Anytime you take the square root of both sides algebraically, you must add the plus minus. And then when I bring the 4 over the other side, it becomes positive, so we have 4 plus or minus, and simplifying the radical will be 2 root 3. And the important thing to understand here is that intercepts are actually points. So this is the x-coordinate of the point, and the y-coordinate, like you would expect, should be 0. So the intercept is actually the point for plus 2 root 3, or the point for minus 2 root 3. The plus or minus means we have 2 of them. So this is one intercept, and this is the other intercept. And notice how we have a value for x, but the y is 0. Now for the y-intercept, we're going to do the same idea. We're going to solve for y when x is 0. So this time we substitute 0 in for x. -4 squared is 16. When I bring that to the other side, it becomes -16. Applied to this means I get a 0. When I take the square root of both sides here, I do have y minus 2 equals plus or minus 0, but plus or minus 0 is just 0, so we can ignore the plus or minus part. And now I add 2 to both sides, I get y equals 2. So that's our y value, which means our x value was 0. So that gives us only one answer here, so our intercept is going to be 0, 2. Make sure when you have a value for the y value, make sure you put it in as the y value and not as the x value. It's not 2, 0, it's 0, 2. All right, let's look at one more quick example of this. They give us this equation in standard form, and they want us to find the x-intercepts. I'm going to go through this a little bit quicker because we're going to replace y with 0 for the x-intercepts because we're solving for x when the other variable is 0. And clean it up a little bit. -1 squared is 1. Bring it over the other side and apply it. It makes that a 9. Square root of both sides gives me a plus or minus 3. And when I bring the 2 over, it becomes negative. And so we have -2 plus or minus 3. Well, -2 plus 3 is 1. And -2 minus 3 is -5. So these are my two answers. And these are the x-coordinates of the answers, which means the y-coordinates are 0. So these are my 2 points. 1, 0 or -5, 0 are the two x-intercepts. And likewise, if we look at the y-intercepts, this time my x value is 0. 2 squared is 4. Bring it over, makes it negative. Apply it to the 10 to get 6. And now I can take the square root of both sides, which gives me plus or minus square root of 6. Bring the 1 over, and you have 1 plus or minus square root of 6. Those would be the two different y values for my points. So since the x value is 0, these are going to be my y-intercepts. 0, 1 plus root 6 and 0, 1 minus root 6. So notice how sometimes you have 4 different intercepts with the circle. And we saw in the last example we had 3 different intercepts. And if you think about it geometrically, you could have no intercepts. You could have 1 intercept, 2 intercepts, 3 intercepts, or 4 intercepts. Alright, now we're going to look at parabolas. And we worked a lot with parabolas at the beginning of the year, but that was more of an analytical approach. And now we're going to look at the geometric properties of the focus of the parabola, which we haven't dealt with yet. But first of all, let's define our parabola geometrically. It's the set of all points, so just like the circle, it is a set of points. It's a set of all points that's equidistant from a fixed line and a point. So if you remember, the circle was a set of all points equidistant from a point. This is the set of all points equidistant from a point and a line. That line we call the directrix, and that point we call the focus. And the plural of focus, by the way, is foci, which we will be seeing when we have ellipses. They have more than one focus. And we still have the vertex is still that minimum or maximum point, and the axis is still the line that passes through the vertex. That is also the line of symmetry of the parabola. And now that we have the focus in our geometric definition, that axis is also the line that goes through the focus, and the vertex will be the axis. Alright, so we have 2 standard forms, one for a vertical model and one for a horizontal model. For the vertical model, and we're talking about which way is the axis going. Either the axis is going vertically, which means in this case the parabola opens upward, or downward if you had a negative leading coefficient. And with the horizontal axis, that if we have a horizontal axis, it's either going to open up to the right or it's going to open up to the left. Now notice these equations are basically y equals x squared. And this equation is basically x equals y squared. So if you forget which is which, you can think of it that way. Y equals x squared is the parent function we used to always deal with, and that's how you can relate it. That was a vertical axis on that parent function. Now, if h and k are both 0, then we do have a degenerate form of these two equations, which can be a little simpler. But notice all of them have this 4p in front of it, where p is the directed distance, and that's important that it's a directed distance from the vertex to the focus. So if you have to go up in our vertical model, if from the vertex, if you go up to get to the focus, that is the direction in which the parabola will open up. So p would be a positive when your parabola is opening upward, and if p was negative, that would put your focus down here and the parabola would open downward. So the sign, the SIGN sign of p, will tell you whether it opens up or down in the vertical model. And luckily, the horizontal model is exactly how you would expect. If p is positive, it opens up to the right, and the focus is to the right of the vertex. And if p is negative, then it opens up to the left, and your focus is to the left of the vertex. All right, let's see all of this in some examples. Here they want us to find the standard form of the equation of the parabola, with vertex at the origin and the focus at 0, 4. All right, since we have the vertexes at the origin, that means h and k are both 0, so we can use our simplified model, which is just x squared equals 4py. Now notice we chose the vertical model, basically y equals x squared, because if the vertex is at the origin and the focus is at 0, 4, that would represent 4 units up from the vertex, which makes it the vertical model. And once we have that, we just need to find a value for p. Well, we should know that because it's 4 units up, then those 4 units, that is your directed distance from the vertex to the focus. So p equals 4. When we plug that in, we get x squared equals 16y. Now that answers the question, because they did ask for the standard form. That's it, where you have it with 4py. So that is the answer, but they might have asked for it in either function notation or explicit form, which just means we would then solve for y. So just to show you the difference there, if we divide both sides by 16, then this equation is equivalent to y equals 1/16 x squared. But just be sure here, they did ask for the standard form, so this would be the correct answer, correct format for the answer. But as long as you recognize these two equations are equivalent. All right, let's look at an additional example, of course. Now here we're given the equations, we want to find the equation. We're given the vertex is 3, 2, the focus is 1, 2. And the first thing we want to determine is what type of model we're dealing with. Since to go from the vertex to the focus, I would actually notice how the only difference is in the x values. That means this is going to be horizontal, because the x values are changing to go from vertex to focus. That would represent left to right, which is the horizontal model. And that equation, of course, would be this. It's basically x equals y squared version of the equation. Now, once we have this, all I need is h, k, and p. Well, h and k, that's the values from the vertex. So 3 would be your h, 2 would be your k, and now all we would need is the value of p. Well, p is the directed distance from the vertex to the focus. So if I look at the differences in the x values there, I'm going from 3 to 1. 3 is our initial point, 1 is our terminal point. So remember, difference in mathematics is always terminal minus initial, which is going to be a -2. To go from 3 to 1, I'm going down 2 units, or I'm going in a -2 units. So p is going to be -2, because again, it's the directed distance from the vertex to the focus, which in this case represents 2 units to the left. And once I know those three values, h, k, and p, I just simply substitute them into our model, and there's our answer. And when inputting them, remember, you can always double check, does my answer make sense? What's the value of y that causes that to be 0? That will be the y value of the vertex. The value of x that causes that to be 0 is the x value of the vertex. Alright, sometimes you're given just the formula, and in this case it's in explicit form, and they want you to find the focus of this equation, the focus of this parabola. And to do that, we do have to change it into the standard form in order to be able to get that value for p. So first thing we're going to do is complete the square. Now, one thing I like to do, though, is in order to complete the square, you can't have a leading coefficient other than 1. So we want to clear out all the fractions, and also we don't want a negative leading coefficient. We want to clear out the negative as well. So I'm going to go ahead and multiply through by -2, and that way we have this equation, which is much easier to work with, no fractions. Alright, so looking at the x's, I'm going to bring the -1 over to the other side, which makes it a +1 over here. And then to complete the square for the x values, I take the 2, divide it by 2, and then square it, which gives me a +1. I have to add that to both sides to preserve equality. And then I'm going to combine the like terms here on the left, clean it up a little bit. And then I have everything I need to write it into standard form. I just need to recognize that this needs to be factored. It's got to be something squared. And then this side, if you notice in our models, the y does not have a coefficient on it. So whatever the coefficient is, you need to factor that out. So here it's a -2. I need to factor out a -2, which will make this, when I divide out -2, becomes a -1, and this will become a +1. But instead of writing it as -1 plus y, we can rearrange them a little bit and simply make it y minus 1. So whatever your coefficient is for y, factor that out. And then this we're going to factor as a perfect square, because it is. And now we have it in standard form. And once we have it in standard form, you can compare it to the model, which is this for the vertical model. Again, that's y equals x squared, basically. And then we can find the values we need. The value of x that causes the x parenthesis be 0, that'll be our value for h, so that h is -1. Value of y that causes this parenthesis to be 0, that'll be k, which is +1. And then since this number outside represents 4p, we can set up the equation that 4p equals -2. And if you solve that for p, you get that p is -1/2. Now, there is a formula for the focus that you can plug into, but I'd rather have you work with the geometric understanding here. We have a vertical model, so our focus will be either up or down from the vertex. Since p is negative, it's going to be down, which means it affects the y values. So we simply take the hk and we apply the p to the y value, which means instead of -1, 1, it'll be -1, a half a unit less than 1, which is 1/2. So I do want you to be able to visualize these and understand them geometrically. Alright, let's look at an additional example of this, of course. Alright, here we have the parabola in this equation. And again, I don't like to work with fractions if I don't have to. So first thing I'm going to do is multiply through by a -6. And when I do that, this is the equation I get with no fractions. And now I'm going to bring the constant to the other side, which makes it a +2. And then for the x's, I complete the square. 4 divided by 2 is 2. When I square it, I get 4. I add that to both sides to preserve equality. And then I can now clean this up on the left. I'm going to combine the like terms, and on the right, I'm going to factor as a perfect square. But then notice that I do have a coefficient of the y, so I need to factor that out. So that'll give me -6 times the quantity y minus 1 equals x plus 2 quantity squared. So now, to find the focus, I simply need the h, k, and the p. Well, the h is associated with the x value, so it's going to be The value of x that causes that to be 0 is negative 2. The value of y that causes that to be 0, which is going to be k, is positive 1. And then I can set up the equation, negative 2 and positive 1 for my h and k. Then I can set up the equation that 4p, from our model, 4p, is equal to whatever this number that we had to factor out is. So 4p equals negative 6. Divide through by 4, you get p equals negative 3 halves. And again, since this is y equals x squared, this is a vertical model, up or down. The negative represents down. So I take this point, negative 2 comma 1, and I go 3 halves units down, so 1.5 units down, and that'll give me negative 2 comma negative 1 half is the coordinates of the focus. Alright, last thing I want to show is the application of these conic sections, specifically the parabola, which is embedded in a lot of modern technology. So if we look at the reflective property of parabolas, we can see that, first of all, we're looking at a light source. If we have a reflector that is in the shape of a parabola, this could be a shiny surface, it could be a mirror, it could be something that's going to reflect the light. When the light source is at the focus, then no matter which direction the light comes out, when it hits the reflector, it'll bounce off the reflector. If we take a look at this one, for example, it'll bounce off the reflector in a direction that is parallel to the axis. So any light that goes into the reflector comes out all parallel to in the same direction. So that intensifies this light. Spotlights are built like this for that reason. Matter of fact, even a flashlight. If you notice that little shiny part around the bulb in a flashlight, it might look like it's a conical shape or cone, but it's really a parabolic shape. It does have a parabolic curve to it, so it can take all of the light and send it all in the same direction, which will intensify the light. And more importantly, for our modern technologies, this also works coming into the focus. So any signal that's coming in parallel to the axis, and we can take all of them, they will all bounce off and go into the focus. So the idea here is for our modern telescopes, the satellite dishes are all shaped in a parabolic curve. They are not circles. They might look circular, but they are parabolic curves, because when the signal comes in and bounces off into the sensor that's placed where the focus is, then it collects all of these different waves, whether they're radio waves or light waves for optical telescopes or microwaves or whichever part of the visual spectrum they're looking for. It collects all of these and focuses into one sensor, which intensifies that source. That's how we can have very sensitive equipment. So these can be light or anything on the visual spectrum, and it also works even for sound waves. If you have any sort of parabolic microphone, for example, that's going to be shaped like a parabola, and you might have seen them in some of the spy movies where they hold up a little parabola dish to listen to a conversation that's far away. The sound waves coming in, again, all bounce off, so it's collecting all kinds of different sound waves, all kinds of parallel sound waves which are from the same sound, bounces them off into the focus and intensifies it where you can hear things with great detail from far away. So a lot of our modern technology uses this reflective property of the parabola. And an additional little property that is good for problem solving, comes up every now and then, is if you have a point anywhere on the parabola and you draw the tangent line to that point on the parabola, then the place where that tangent line intersects the axis will create a point that is the same distance away from the focus as that original point on the parabola. In other words, the distance from P in this diagram to the focus is the same as the distance from the focus to that intersection with the tangent line. So these two distances are the same, which creates a nice little isosceles triangle, which means that these two base angles in an isosceles triangle, denoted by alpha in this model, are also going to be the same. So if you know that property, then you can set up that triangle, which can help you sometimes solve problems. So these are the very useful properties of parabolas that make them embedded in the modern technology. All right, and we're done.